Next presenter is coming to us from Zoomland. Catherine comes to us from Johns Hopkins University Applied Physics Lab. She is a program manager for Advanced Autonomy Test and Evaluation within the C Control mission area of the Johns Hopkins Applied Physics Lab. Her primary focus is guiding the DoD towards full scope understanding of what autonomy T&E truly provides, such as validation of modeling and simulation techniques, development of test tools and technologies to improve T&E within M&S environments, data collection, analysis, and visualization to make smarter decisions more easily, improvement and streamlining of the T&E process, to improve test, fielding, and understanding of measuring trust and autonomy, supporting rapid experimentation and feedback loops from testing via M&S to testing via physical systems. So thank you so much for being here, and her talk is on T&E landscapes for advanced autonomy.
So as stated before, and please let me know if you can't hear me again, my name is Catherine Lehman. I'm the program manager for C Control's Advanced Autonomy Test Evaluation over at Johns Hopkins Applied Physics Lab. Today, I wanted to provide a bit of an overview about what the larger landscape of autonomy T&E looks like for the DoD, specifically for autonomous systems. I want to give this at like that 5,000-foot level view. I'm sure many of you in the room are technical experts in one or many of these specific areas, but may not necessarily see how these different areas may tie in or impact other areas or the larger scope of the T&E landscape. In addition to that, a lot of the work that we do here at APL isn't openly shareable with, I'm sure many of the organizations here are the same. So the slides from the discussion really is kind of tampered down to support the open source discussions that we have here. But if you do have any questions or want to talk into more detail, then please don't hesitate to reach out to me. I'd be happy to speak out with anyone more fully about anything. Before I continue to the actual slides, I just want to do one more confirmation. Are we good on the audio?
We are good.
Perfect. And can you guys see my screens?
Yes, we can.
Perfect. Okay. So I'm sure all of you are aware that the DoD is making major investments into developing these large-scale autonomous systems. It's going from basic research from groups like ONR all the way through major acquisition programs. And in this brief, when I'm speaking of autonomous systems, I'm really talking about those really fully complex autonomous systems that is more than just the generalized components that are used to fit within autonomous systems. So it's more than just the individual path planning or the vehicle controllers, but rather the full encapsulated decision-making system. And when it comes to those type of systems, we're still trying to find out how to integrate them within the field and how to optimize our capabilities. A major goal that the Navy is looking to support is multi-domain distributed operations, utilizing multiple different types of systems together for a single mission. And the problem, though, is that we've got visions for how this would work, but we really don't have an idea for how these systems will run in the field, how they'll be implemented, or when. So APL largely focuses on the Navy, but we work across the DoD within this domain, and we see a lot of common trends and bottlenecks when it comes to the concepts of fielding and testing these capabilities. And largely, one of the things that we're looking at is how are they going to appropriately test and certify these systems before going out into the field. If I broke down some of the major concern or the stress areas for what is hindering the ability for testing and certification, there's really 4 to 5 major areas that we see. The first one is being able to support validated cross-autonomy capabilities within modeling and simulation environments. I think that one's a huge one, is going to be a major crux for how we move forward with test and evaluation of systems. In addition to that, within modeling and simulations, and then other operational test constructs, building the technologies that will be able to support the full testing across the range of applicabilities, and streamlining those capabilities in a way that will allow for faster, more structured test flows as you move through not just development through operational tests, but through a construct of the live virtual constructive aspects that you see that is being used a lot today. And in addition to the flow of how we're testing and the test tools that can be used to help facilitate those, two major areas that go across those considerations really is data, how we're storing it and accessing it, and analyzing it so that way it's able to be used for proper decision making. And then finally, the trust and calibration of stakeholders. And I specify stakeholders rather than users because it's not just the end users that we really should be looking at in regards to trust and how that's measured and used. So the rest of this brief really kind of is bound by these 5 sub-bullets, and I'll go into a little bit of details for each one. So the first one is modeling and simulation. I think that it's well known that that's really going to be critical for testing today's autonomous systems really at full scale. And just to give a little bit of, just a scoping of why it is so important, I think it's important to see how the growth of autonomy and how it's going to be fielded really kind of shows about how complex it really is. First, we start looking at the autonomous component in its own. You've got one system that is doing a specific tasking, such as path planning or mission planning or obstacle avoidance. That can have its own level of complexity depending on how it's written or the type of decision modes that is built into the system. But then you take that individual component and then you put it into an integration with multiple other autonomous components to build that fully encapsulated autonomous system. Once you have those, you're looking to see what kind of tasking that they're expected to be able to do and what could they be done in order to complete the missions that they're given out to be able to do. And with autonomous systems today, a lot of times the decision making is going to be non-deterministic, and that they're going to be dynamic responses based on the environments that they're put into. And these environments are going to be more and more complex the further we go up in the chain. We can go into more simplistic testing to make sure that they can complete a specific task for a specific area. But once you start going out into that complex, realistic field, the complexity of the environment becomes compounded more so. With that, you really have to start looking at, there may be non-deterministic responses that could be dynamic, but the number of outcomes that could be successful will then also increase. It's not just saying whether the system is going to do a complete task and then have a specific outcome and then it's is or is not correct. There may be multiple beneficial or successful outcomes that may occur. You need to be able to test and assess whether or not they made the right decisions in the right ways. And then you start going into even more complexity when you have the concept of multiple distributed operations with different autonomous systems or with dynamic teaming with human agents into that. And again, it just compounds itself. And you really start to becoming aware of the state space explosion, where there's a huge number of tests that can be run. And it's going to be unrealistic, even within modeling and simulation environments, to really be able to test all of those constructs. So when we start to go into that, we understand modeling and simulation is going to be a need. There's the only way that we're going to be able to test everything or even get able to be close to testing everything. But I think also another key area that we should be looking at is being able to ensure flexibility within the simulation environments. There's some things that we have to make sure that we are always going to be on top of that's not flexible, making sure that we have accurate data that is of high quality, but we do need to ensure that we've got appropriate scalability. And the reason why I'm specifying this is for multiple reasons. The most obvious one is developers and vendors are creating these autonomies and they're developing simulation environments to meet the needs of what they are building and testing to be able to maximize on the benefit that they're providing while minimizing the amount of burden and resources that they have to use to be able to do so. So depending on what type of autonomy you're doing or what type of models that you need, it could go from very low fidelity requirements for a simulation environment or the models used in it, all the way up to extremely high fidelity, very visualistic types of simulation environments. And each of these types of environments have their pros and cons to them when it comes to test and evaluation. When you're looking at being able to take huge swaths of test runs, being able to run them in bulk, multiples at a time, faster than real time, often the lower the fidelity of the model, the lower fidelity of the simulation, the faster that they can run because they don't have the burdens of the resource constraints. That being said, you're not going to be able to get the full detailed end-to-end type of test and enrichment that you would get with high fidelities. So if we can look at scalability in a way of maximizing what you need to do to possibly having lower fidelities for the large scale testing to be able to find those areas of test bounds that you really want to focus in on and then start increasing the fidelity of the environments in there, then we can really start to say we're maximizing the amount of use and the resources to really focus in on what we need to test and then going into those very, very high level simulation environments that may be at real time, that may require the visualization for those select tests that are of most importance to that. But you're utilizing those environments once you've already determined that you can trust that the tests that you are selecting are valid and are the ones that you actually want to take that time to really look at and assess. So with every kind of suggestion or movement forward, there's going to be pros and cons. And one of the things that is a big con and was probably a major roadblock for adding in multiple different types of environments for testing across the scales is integration. I will be the first one to tell you that integration is absurdly hard in today's environments. Each autonomy, each test tool environment and simulation requires specific integration tasks that are readily repeatable and are applicable to other systems. You've got the major components that can be the same, but in many of the tool sets that we use to integrate with different simulation environments, the largest hole in the tent there is the integration effort for each time we're going through it. So I don't know how much everybody agrees that standardization is the way to go to things, but it is going to be a common thread here that I have in my brief with the caveat of standardization with flexibility. I think that the idea of standardization is going to be huge and super beneficial, especially as we start going into the concepts of modularization. Modularization provides the ability for the flexibility. You use the things that you need without taking in the burdens or the costs of the items that you don't need. But at the same time, the requirement for them to be standardized, integratable, interchangeable, and scalable are going to be absolutely required. The DoD is very aware of this, and there's a lot of different efforts that are out there today. I'd be more than happy to speak to those more specifically and what APL has done to help support those. But just a couple of examples, specifically from the architectural side of autonomies and interconnecting autonomies to other systems or other environments. Some examples include HLA, or the high-level architecture, to be able to connect multiple simulations and multiple fidelities. And then the UMA standardization, or the unmanned maritime autonomy architecture, that allows common writings and message types for different types of services when different models or simulation environments are connecting to different aspects of specific autonomies. So again, with this being more of a distro A, I went out and did some research. Standardization, modularity is not unique to the DoD, nor is it unique to the commercial world, but there are some really good standards out in the commercial world that I think that could be utilized and be leveraged for the DoD. One example here, and I'm sure that it's kind of hard for everybody to see, but this is an excerpt from ASAM, which is the Association for Standardization of Automation and Measuring Systems. It's a nonprofit organization, and its main goal is promoting standardization for tool chains, largely in the automated development and testing areas, but I think a lot of lessons learned for how we're developing testing, to what level of testing, and the type of test tools and capabilities that can be used to create that full matrix of end-to-end test flows. Documenting them and tracing them could be really useful for these type of standards that you can see out commercially. the DoD, again, is doing work in this realm, and a lot of focus on open architecture for being able to create test tools that can be used interchangeably and interoperably is being done. One of the biggest ones that we see today is with PMS 406, their autonomy rail effort. Rail, I think, is Rapid Autonomy Integration Lab, where they are looking to create a means of test and evaluation for different autonomous systems more quickly, but still requiring the base minimum expectation of what would be needed for quality and the testing for certification purposes. And I apologize for my cat. So going into, the idea of scalability and modularity, I think it's also really important to show that it helps with building these different types of testing environments, and it helps with building the right level of simulation needs or the right level of tests at the right time. But it's also a prime component for different testing constructs that are really being utilized in today's environments, specifically the live virtual constructive testing environments, where you go from a modeling and simulation based capability for, again, that larger scale testing approach to really understand what the state spaces look like and where you want to focus in on more integrated tasks with the software in the loop to the hardware in the loop, all the way up to having the full fielded systems within field testing. And modularity will really be able to help do that, but not without the standardization that goes behind it. Some really good examples of uses for LVC constructs and development processes today. You see a lot with autonomous aircraft systems and developments. They often require test beds that need to be able to have smooth transitions between developmental test, operational test, and fielding, and being able to show not just the testing within certain bounds, but demonstrations of these very large and very expensive platforms and the field testing capabilities. And then in addition to not just the LVC environments that we're looking to be able to run these tests in, but it's also really important to see what kind of technologies can we build today that helps support the testing of these autonomous systems. Again, they're going to be extremely complex, and with the number of test runs that we can do within modeling and simulation, the amount of data and the amount of output that we get from those is going to be overwhelming, and being able to create capabilities that help appease the burden for testing groups, I think, is going to be extremely important. And so that's where we go into what kind of test technologies can be really useful. We're looking deeper now into not just what tests can we run, but how are we running these tests? And again, the same that we saw with the more lightweight modeling and simulation environments, I think that the same can be said for the autonomies themselves. The more lightweight an autonomy can be, as well as the environment it's run in, the faster we can do those bulk testings across the gambit of state spaces. Tools like APL's range adversarial planning tool, which you're seeing an example of how it can be benefit in the top right video, it really looks at utilizing adaptive sampling techniques over the global sampling techniques that you see more often. And this allows for the faster discovery of performance boundaries more quickly and with fewer sets of bulk runs that are needed. So that way you're really honing in on what areas that the autonomy may or may not successfully run in, and how that may change from a pass to fail based on small variations in the state spaces or the variables that can be changed. And then that way you can ignore the swaths of area that are very specifically a positive test run, or all the areas that you know that the autonomy will not run in, but really focus on why a system passes or fails based on very small changes in the operating environment that it's running in. And then as we find and identify those specific tasks, then we can go and build into higher fidelity models and simulations that require high processing power to be able to get more in-depth assessments and individualized tests for those. But one of the concerns that we have as we go through with the concept of running these bulk tests is not just about the modeling and simulation environment, but it could be concerns or constraints from the autonomies themselves. There are a lot of autonomies that are just as bound to computational power and time to execute that the modeling and simulations may have constrictions on. So we're also looking at means to developing test tool capabilities that can help create lightweight surrogates of a complex autonomy that can at least capture and replicate behaviors of an autonomy within a complex environment. So that way you can utilize it in these lower fidelity models through tools like RAPT to be able to get that large swath of testing in a much faster and lighter way that you may not be able to do if the autonomy itself requires a lot of computational time or power to be able to execute, if you can use these surrogates instead. And then as you understand those tests that you want to get more fidelity on, then you start integrating that more complex autonomy into the system. And then finally, you can move forward into the farther to the right side of the LVC construct, into the live testing area. At the bottom center, we have a screenshot from APL's TASE efforts, which is largely creating a geofencing area for physical test spaces for air domain platforms. So that way, as the autonomous system runs through individualized tests, if it goes past this geofence area, then there's an override that will allow the system to end the mission and then safely stop the test and ensure that the assets are safely landed and completed. These are just some of the type of test technologies that we do here at APL. And again, I'd be more than happy to continue to talk about that in a different setting for anyone who's interested. But these are just a few examples of some of the types of test tools that can really be used to extend the capability and the benefit of testing environments for these autonomous systems. And again, I want to ensure, everyone here, with this being a distro A brief, I'm being purposefully vague on some of the technologies and the applications. And I don't want to diminish the fact that the DoD and many of the groups of, that you are all part of are actively working these things in the DoD. Some examples that I've been able to pull up just from simple Google searches that APL has helped with producing with these live virtual constructive test environments, as well as developing test tools, includes across the DoD, such as Army and Air Force and Navy. Navy is largely one that I'm most familiar with being in the sea control mission area. But I also know that there are other ones out there that other groups can certainly help. If there's any questions about other aspects or efforts for LVCs within the DoD, please don't hesitate to reach out to me, because there's definitely more than what I'm able to discuss here in this forum. And then going into the last couple of bullets that was previously in the beginning part of the slide deck, I think that there's some linchpin concepts that really goes across all of those areas of the T&E landscape, and data is a massive one. Especially when you're looking at the testing of these autonomous systems, autonomies are hugely complex. They're going to have a huge amount of data to build and to deploy, and the outputs that they need and the outputs that they provide are going to be very complex. But then when we start adding in huge amount of test data, we are just compounding the problem. There needs to really be tools and methods on the back end of testing that will allow people to easily take that data, parse it, and review it in a way that makes sense, and to allow them to make the proper decisions and feel confident in the decisions that they're making without forcing those decision makers to be machine learning experts or statisticians. So with that in mind, I have a few slides that really kind of talk about the concepts of collection, quality, and data visualization, and what should be really considered when you're looking at them. So again, we're going to be creating massive quantities of data, especially when you're adding in complex decision-making capabilities for these systems. There needs to be methods and procedures for how we're managing, handling, and analyzing data both at the local individual test level, but also as well as a larger scale of T&E. One of the things that I think I talked to a little bit later is the concept of data accessibility and data sharing. I think that we all know from, preschool and elementary school, sharing is caring. And I think it's the same that goes across here, where if we can provide data that is accessible to multiple groups and is done in a way that's formatted appropriately and accessible and stored in a way that supports the concept of big data and sharing for that, I think that it'll really be able to catapult us over to a next step. But that being said, we need to make sure that these things are being done appropriately to ensure the quality and quantity of the testing data across the life cycles, especially when you may be using some data for one level of testing. You want to make sure you're not necessarily using that same exact data for another level of testing. So also tracking the data in addition to storing and formatting it is going to be extremely important. And then in addition to access and storage, the quality and quantity and provenance of the data that's being stored and used is going to be especially important. Specifically speaking to training models and testing data, the training and testing data has to be different. You don't want to train to the test. And the ability to access real data sets can be really difficult, especially in these secret or top secret environments. And oftentimes we're simply not able to get enough data for what's needed for just the training, let alone the testing after the fact. So going back to the previous slide with the concept of access and storage, we now need to look at managing and tracking how the data that we do share is going to be used, but we also need to make sure that the data is reliable and of high quality. As we go through this, largely it's not even necessarily where the data comes from or how it's formatted, but especially when it comes to autonomous systems, these data sets are going to be labeled, they're going to be processed, and they're going to be manipulated in different ways and multiple times before it's necessarily used for training and for testing. So there really needs to be some level of process quality requirements and oversight or standardization that can help ensure that the data that's available is being properly traced, is quality checked, and that we're using it as appropriately as possible, especially because even though data is in mass quantities, it is still not enough for us to be able to get the job done. And so with the concept of the fact that there's not enough data to go around and it's going to be difficult to share appropriately, a lot of work is now being done on, test tool capability, training tool type capabilities. And one aspect of that is the generation of synthetic data. A lot of groups are using synthetic data that they can label and use to train these models that are going to be out in the field. But then in addition to that, creating more synthetic data that is used to assess whether the model that's trained is going to be usable out in the field when looking at real data sets. And so that adds a whole level of complexity that builds on top of what we're already facing. In addition to whether or not the synthetic data is good enough to the real world and whether the system would act in the same way with synthetic data that it would with real data, synthetic data also is just as prone to the same other issues as real data. So we're adding more and more complexities where we're going to need more test capabilities and more technical capabilities to be able to ensure that we're building the infrastructure to properly allow and support the use of things like synthetic data generation as it becomes more prominent. And then lastly, when it looks to data, I think that one of the huge things, a little bit more about my background is I'm a human factors engineer originally by trade. I have my master's from human-centered computing, and data visualization and making sure that we are providing the end users with the means for making the decisions that they need in a way that's best usable for them is extremely important. Again, needing data for testing and training the algorithms is a large part of data collection, and the need for analysis and decision making is probably just as important as the ones for creating the systems. Those responsible for doing the assessments and certifications often aren't going to be developers. They're not going to be machine learning experts or statisticians. And I would argue that they don't necessarily have to be able to say that these systems are reliable and trustworthy. Data visualizations and proper metrics and measures development really is going to be essential for maximizing the benefit of the data collected and how it's being processed. We need to ensure that the right data is presented in the right ways that can provide insights that allow the decision makers to trust the system and trust their decisions for moving the system forward, especially for those that really are signing their name in blood for when something does happen down the road and, Congress or the lawyers go to that person's name who's on the dotted line. So they need to be able to make sure that they can confidently sign that these systems can be fielded. The easier it is for those types of people to be able to understand the data and understand the complex topics and tasks that are being worked through, the easier it will be for them to trust and rely on the system itself and be able to confidently make those decisions. And then that really kind of leads to the last of the biggest set of topics that I think are most important. And again, just within this 25-minute capability time, or this 25-minute time that I have, is trust. Trust really is a huge buzzword today, and it can mean a lot of different things to a lot of different people. But the impacts of trust starts from the far left of the life cycle. It starts at the ideation, the requirements development, through who's making the determination of how it's being funded and how important it is, through the development, the testing, the T&E, the training, and the operational use of these systems. A lot of times we really look at the end users, the warfighters, as the user that has a requirement for trust. And I don't argue that point. It's probably 80% of what's really there. But I emphasize the concept of looking at trust from a stakeholder perspective, because it's not just those end users. As we talked about in the previous slide, it's the decision makers, it's the testers, it's the ones that have to trust that the system will be beneficial for the warfighters that are being able to provide the funding. It needs to be able to be trusted by the program managers that are determining how it's going to be developed and what does or does not hit the cut when, resources become tight. And so really looking at trust from the view of the different stakeholders across the life cycle, I think is going to be extremely important. And they've got multiple dimensions that can impact whether each stakeholder has trust, how much trust that they have, and how much the trust that they have impacts their decisions, which could therefore have, that snowball effect moving further down to the right, and how their decisions or their trust on the system impacts the downward effects when it does get into the operational field. So it is a hugely, hugely complex area that is not just within the test and evaluation realm, but really is much, much more larger scale. And it should probably be addressed to the same level as data quality and resource management across the DoD when it looks to fielding these systems. And, as with the speaker that we have earlier, right before me, talking about situation awareness, there are a lot of initiatives that look to address that, but so many of them are currently still in the realm of research. And there's very little that's moving the ball forward for application. And APL is working with multiples of these groups and working on multiple efforts of trust. And this slide is specifically an excerpt from one study that my team is looking at to look at this landscape of what trust and what it means through these various lenses in order to hopefully understand where trust has the biggest impacts, who should really be looking at trust, and how do we mitigate roadblocks to trust across the life cycle, so that way we're optimizing it for the large and long scale. And then with the very limited time that we have, that's the majority of my brief today. I know that there are huge areas that I have not even touched on in regards to T&E and support. How do things get affected when you have learning systems that are changing algorithms in the field? How do you look at, continuous and iterative methodologies of T&E? across the life cycle and after. Cybersecurity, resilience against, the different complexities that may exist, staffing, skill development, STEM outreach for T&E in these autonomous systems, and ease of entry into, the development of T&E are all very important areas that should be addressed, but just we don't have time in the brief time that I have for today. But again, if anybody is interested to talk, I am more than happy to have those conversations, and please come to me with any sort of topics or ideas you want to bring up.
Thank you so much, Catherine. I think we are out of time for questions,
Sorry.
but as she said, please reach out. It's what DataWorks is all about. It's networking.